I'll try. Thank you so much, first of all, for inviting me. It's a great honor to be here. I hope you will enjoy the talk. It's a joint work with my former advisor, Rafail Ostrovsky. I started it when I was a student at UCLA. Let me begin with sort of a picture that will explain what we're doing. I will not talk about motivation so much, but feel free to ask me questions after the talk. I will also skip a few technical details, but if you want to talk more after the talk, I will be more than happy to give all the details. So imagine this is a problem that we will discuss. Imagine that we observe a sequence of marbles of different colors, and they come as a stream of marbles without any particular order, or we cannot, we don't know the order ahead of time. At the end, what we have is the frequency vector here, right? So for each color, we essentially can count how many marbles of different colors we observe. And our objective function is the following. What we want to compute, basically, if we would have the ability to store this data in our memory, if we have sufficient space, we would like to sort the data like this by colors, compute the counters, then given some sort of function z of x, we would like to modify the frequencies. In this case, we will consider the case power of the frequency, and at the end we want to compute one number, which is the aggregation. Okay, one number which is the sum of all this frequency taken to the power of k. Okay, and this is what we call frequency moment. Okay, is this clear? What? Okay, great. So this is what we want, and this problem was introduced in a seminal paper of Alon, Matias, and Szegedy in 1996 that won a Gödel Award in 2005. Formally, the problem is defined as follows: given a sequence of numbers of length m, and numbers are from 1 to n, a frequency of a number is defined by simply as the number of times that we observe this number in the stream, in the sequence. And the case frequency moment is this sum of case powers. Okay, so that's again I'm just repeating what I just said. Our goal will be to compute a random number such that the probability that this number is in 1 plus minus epsilon approximation of the moment is sufficiently high, some constant, 0.9. That can be as usual amplification changed to any delta. And what makes this problem non-trivial, of course, as I just showed in the previous slides, if we could make many passes over the data, or if we could store the entire data in our memory, then it would be trivial to compute it precisely. So what we want is a single pass over the sequence and a sublinear space. Okay, so space should be it allows both the number of the length of the sequence and the size of the universe. Okay, so this is the definition of this problem, and it has been a lot of work on this problem. I will not talk about what has been done for a small case, for the case of the second frequency moment. I will just mention that it has been solved already for the k larger, smaller than 2. What I will discuss today is this case of a large frequency moments when k larger than 3. And unfortunately, it is frustrating that we still don't know what is the right answer up to this moment. Yes, so I assume that epsilon in this case is a constant. So just this is a space. This is all space bounds, yes.
But it's still one pass.
This is still one pass, yes.
And what's the minimum space bound?
Yes. All right, so in this case, this is what we give. It's roughly a log n improvement of what is known before this work, and the lower bound is still n to the 1 minus 2 over k. So this is what I will present. C I will explain in the next slide. This is a iterated log basically. Okay, so to be more specific, we give the following bound n to the 1 minus 2 over k log n, and for any constant we give the iterated log for this constant. Okay. We make the following assumptions: that epsilon is a constant, and the length of the stream and the size of our universe are polynomially far from each other. Yes. Yes. N to some power. Yes. Yes. Vice versa. But
so roughly speaking, if n to some, if k was about log n, k was the moment was about log n, then the gap is between linear space and
yes.
log n space.
Yes. Okay. All right. So I will talk now about the main idea. From now on, I will talk about the solution. The main idea is the following. So as I mentioned, the improvement, the rough. Please. Sorry.
So you have the assumptions epsilon k of 1. What can you say something about the k? Say that k is log n.
Well, the bound still will be the same bound, so k will be there. I don't see. I will need to be precise. I will need to look at the proofs. Right. 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 Yes. Yes.
So for k equals log n, there are no results that are better than what follows easily.
Yeah, the low bounds communicates complexity. And what did you say about the approximating?
Every high the type just maintain all.
Oh, yeah, that's the n log n. So yeah, that's something like that.
So that's more interesting.
But yeah, right. Yes. Should I go? Okay, so roughly the main idea of our algorithm is the following: that the previous methods use some sort of a sketching to find heavy elements to approximate. I will explain in the next slide what exactly is two main steps of our algorithm, but the key idea is that we don't need to apply union bound to get an approximation of elements, because given the trick that I will show, the sampling, pick and drop sampling trick, we can always guarantee that our estimation that we produce is an underestimation. So, and this basically in one sentence, this is why it works. Okay, so we don't need this extra log n factor that we usually need when we apply union bound on n elements. Now let me talk about two steps separately. Basically, this is not a new approach. This approach is known from the paper of Dick and Woodruff, and the approach is the following: that first we look at the frequency vector and we find if there is any heavy element, if there is an element that captures a non-trivial fraction of the total weight, and if there is, we would like to find it and approximate with good precision, with good probability.
Don't look at the vector. That's what we would like to do.
Yeah, right.
So anyway, that's the definition of a heavy element.
Right. Yeah, I will look at the stream, and then by looking at the stream, I will.
So you would not know this, but that's the definition of what a heavy element is.
Yes.
And it's a good idea to find. Yeah.
Right, and then using this algorithm for finding heavy elements as a black box, we would like to approximate the case moment as well. And so basically, the iterated log comes from here, and the rest of the bound comes from here. Okay, so I will start, and this is the most interesting part, so I will try to explain this portion and give some proofs at the end.
So if there are no heavy elements, it's all the material.
Yes, yes. The rough idea is that there are no heavy elements, and we can basically reduce the dimensionality of the vector without paying much. Basically, if, for example, everything is 1, then all the frequencies are 1, 0. So the first step will be to just visualize our problem as a problem on matrices. And so imagine the case when we are given some parameter r, and imagine that the length of our stream is exactly the product of some r and t. Then we can represent our stream as such matrix. And so from now on, I will basically talk about this matrix. So the first piece of the stream becomes the first row, the second row, etc., etc. Okay, that's clear. Here is the intuition. I will basically explain the main idea on the slide, and then I will talk about the general case. Imagine the case when our frequency vector has exactly one heavy element, and for the sake of this example, it's 1, and all other frequencies are either 0 or 1. Imagine also the case, and we are lucky, and when we do this splitting of a stream into a matrix, we observe this, the 1 appears exactly in one row, every time appears in one row. Then basically this is where the gain comes, right? So now the probability to catch 1, if we just sample independently in each row, becomes higher than if we would do it on the entire stream. At the same time, it is easy to check if there is a duplicate or not, right? So there is an easy test for heavy element in the following sense. Sample in the row, check if there is the same element in the next row. If you find it, then this is your heavy element. If you don't find it, just drop the sample and pick the next one. So when we will read this stream of data row by row, and every row we will choose the next sample, just one of them, yes. Check on the next row whether or not there is a repetition. If there is a repetition, we are done. We will just announce that this is a heavy element. If there is no repetition, we don't need this sample anymore. We will just yes. This is exactly why we need this general case. But first I wanted to illustrate the main idea. Yeah, but you're absolutely right. We need to show how to do it in general. Yes, please.
Do we have as much access to the input as we want, or is there some limited number of passes?
One pass. Only one pass. So you only read it once. That's it. Okay. Make sense? Okay, so I just wanted to, this slide, I just wanted to illustrate the key intuition of this. So everything else will be generalization of this simple idea.
But you call something heavy if you find it in the next row again.
Yes. So for this, so let's call it, this is a promise problem. Right, so let me even go to the next slide probably. This is specifically considers the following promise problem, that we have exactly one entry, which is either its frequency either n to the 1 over k or 0. The adversary can choose this entry, and all the rest are either 0, 1. Okay, so now to be more precise, right? Excuse me. Oh, this means that the number of non-zero, this is the 0 moment, the number of non-zero elements are sufficiently large. It will work without this assumption as well, but just to illustrate this point. Yes, right. So imagine that in this case we split this stream, this is our stream, we split it into intervals of lengths approximately sorry, 1 n to the 1 minus 1 over k, and we sample do exactly the same trick that we did in the previous slide. Then it is not hard to see that the probability to sample I in at least one of these rows will be this. It will be 1 over 2, 1 over n to the 1 minus 2 over k in at least one of them. Why? Because we have the length of this row is this. If each one of them appears exactly once, so that's an easy computation, right? So we need approximately this many samples to find it. So the number of samples will be n to the 1 minus 2 over k to find the heavy element. Okay. And so if we would only need to solve this promise problem, this is a solution to the promise problem. This is the entire solution. Yes. So I will just run that many samples with a constant probability. One of them will be what I need. Everything else has a frequency either 0 or 1, so I will discard it. There is no confusion, no noise. And I will find it with a constant probability. My space will be n to the 1 minus 2 over k log n, or log m. Just to store log n bits. Okay? So this is... So the length of the row will be n to the 1 over k. Yeah. The problem with that, basically, it might be the case that there will be no duplicate in the next row or in the next couple of rows, right? Okay. So you will have to store many samples.
You just need to distinguish 0 or 1 from very large. Okay. So you don't need to find all duplicates. You just want to know who is the guy that
but you can afford it, so why not?
Well, you can afford it if you change the size of rows and columns.
Right, but why not do it? I mean, what's the cost of using shorter rows and...
Well, how would you recognize if something is...
If you have a shorter row, then it's not that this trick will not necessarily work, right? Because you cannot promise that there will be duplicate in the next row, so you probably need to keep it for many rows, and it means keeping for many rows means basically multiplying your space.
Oh, I see.
That's the reason. Yeah. So the key trick again is that whenever we don't find a duplicate, we can just drop the sample. Okay. So at any moment, we will maintain exactly one sample. Two, basically, the current sample and the sample from the previous row. Yes, please.
Do you know for this particular promise problem, where there's one heavy element for n, whether this n to the 1 minus 2 over k is also a type low heavy?
Yes. It's as far as I remember, yes. So this problem is sort of, to some extent, the hardest case for this.
But you asked whether the lower bound can be improved.
No, just whether it's obtained by this type of...
But this is already n to the gap between the upper and lower bound is still log n.
Sure. I'm just... Well, he stated the lower bounds for the general problem, but not for the specific promise problem. It sounds like...
Oh, I see. Okay, yeah, good.
Yeah, I think the lower bound comes exactly from instances of this kind.
Yes. 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 So this is one of the reasons, yeah. We want to consider it here. The reason we started with this promise problem is because, yeah, the lower bound comes from it. Okay, so and as the general case is what it makes it non-trivial, of course. So, as Noga said, what if someone puts many ones at the beginning, or there is some noise in general? Like, why would it work, and what should we do in this case? So this is the most probably. So the general algorithm is not significantly more complicated than what I have shown, but it requires some extra notations, and well, unfortunately, I will just go back in a few slides. If you don't remember what these numbers are, just let me know. So d sub I j basically, so imagine that we have a matrix. D sub I j is basically the tail frequency of an entry that is located on at ij. So for example, if this is ij, then the tail frequency will be 2, right? So how many times I see the same element in the remainder of the row, including this column, all right? And then the only thing that new that I introduce is the frequency of an element in a particular row. So basically it's the same number that is split rows by rows. So this, I'm sorry.
So it's not the matrix we saw before.
It is.
But you said the number is the frequency, the number of times it appears in the remainder of the row.
Yes.
It's not, I mean, the matrix before just contained the element, just contained the string. This is not the string.
This is the stream.
Oh, this is the string.
It is the same. It is the same stream. Yeah. I'm sorry. This is exactly the same matrix. This is just a more general case where something can appear more than once. Right. So as in this example, what we have, the third moment, for example, is 187, and basically this is r. R will be 3, so the number of rows is 3. The number of columns is 4. The only other thing before I proceed that I want to mention is that I will assume, for the sake of our analysis, that 1 is a heavy element, and so we will try to find this 1. So it will be arbitrarily distributed, but we will try to find this 1. So and so for the notational purposes, G sub k will be the frequency moment, the residual frequency moment, everything except this first one. So this is the algorithm. The algorithm is basically a generalization what we have seen so far with 2 additional parameters. Parameter number 1 is lambda, just a number. Parameter number 2 is basically the number of rows. So if we have our stream and we have a parameter that specified what will be the number of our rows, it defines the interval, right? So if we assume that the length of the stream is divisible by this number, then from now on we will consider a matrix with r rows, and in every row what will happen is it will be the following. First of all, in every row we will choose a random index for a column. Okay, so basically we will choose, so what you see there, I sub j is a column, a random column for every row. And then in every row as well, we will basically, this will be our sample, so we will sample this element, exactly what we did before, sample an element, and we will count the frequency, the tail frequency, how many times we have seen this element in the remainder of this row. Okay, this is the same idea that was used in the paper of Alon, Matias, and Szegedy, just they used it for the entire stream. So when you sample, you count until the end, as far as right. Yes. So here we do very similar thing, but just for each row. And now, so imagine that we have these numbers. Imagine that this is offline, so no streaming, just for a second. So we have for every row, we have a local sample and a local counter, a little s sub I and a little c sub I. From now on, we will play the following deterministic game. There is no randomness anymore. We will choose one winning sample. So for every row, we will look who will win at the end of this game. We will start with the first row, and then every time we will move from row to row and see if there is a local sample that will win in the following sense, that the counter of the local sample is larger than what we have so far, or, and this gives basically a chance for someone who has a lot of elements in one row to win, to become a new sample.
So
Or
you're just trying to find this deterministic strategy that uses a lot of
yes,
elements in
yes,
the same row.
yes, yes, absolutely. This is exactly.
Parameter lambda is just a threshold.
The parameter lambda is we need it for the following case. Generally,
What the Q's are, so maybe you can.
yeah, right. Just a second. Q is basically the liveness of the sample. So I want to address two things. First, if there is an element in the row that have a lot of repetitions, I want to give him a chance to be chosen, and this is what we have here. Q, this is exactly to address the noise. Imagine a case when we have, in the first row, we have everything filled up with some false positives. For example, we have elements that frequency n to some alpha. Okay, so they're sufficiently large, polynomially large, but they're not sufficient to contribute to the frequency mount. So this Q sub I is basically the number of rows that we allowed to maintain this sample. What we're saying is that the frequency, the counter for every element must grow at least linearly. Okay, so if after if after a certain number of rows this value is small, we will drop the sample. So basically, if we have n to the alpha, if we have an element with a frequency n to the alpha, we will drop this element after n to the alpha rows. We will not leave, we will not go with this number for until the end. So it is not enough to have a high frequency to win with higher frequency than everyone else. You also need to maintain some linear growth of your frequency. Does it make sense what I'm saying?
So if some element will be very popular only in the first row, it will be chosen at the beginning and it will be dropped.
Yes, absolutely. This is exactly the idea.
What would be lambda when you show the slide?
I will show in the next few slides. This is the lambda. So essentially what is important here is the ratio between the moment, the case moment, and the first moment, and the length of our stream. And the problem will be that we don't know this ratio. So the number of rows and the number of columns, it's really a function not only of the length of the stream, it's also a function of the case moment. If the case moment can be very large, right? Can be significantly larger than the length of the stream. And in this case, we need to separate this differently.
I see. So you will try in parallel make many choices of R.
Yes, absolutely. Yes. So R should be chosen as a function not only of the length of the stream, but also as the actual value, which we don't know, the value of the frequency moment. If we would know the value of frequency moment, we would be done. Right. So this is. It is sufficient to run a log n, but yeah, but you could do it logarithmic.
So lambda is defined as f. So f1 is just the first moment.
Yes.
What you denoted before by n.
Yes. Yes.
That's something that's known.
Yes. That's, you can assume that this is known. we can work even without this assumption. So that's
Are we looking at several matrices now, or just a single matrix?
so what will happen at the end. So let me try to explain. This is the algorithm for a single matrix. So if you know R and T, then this is the algorithm for a single matrix. And we will prove that if there is a relation between a heavy element and the third and the second moment inside this matrix, then at the end, the result of this algorithm will be what we need. Okay? In our stream, we don't know what these values are. We don't know what is the right value of lambda, and we don't know what is the right value of R. Therefore, we will have to apply it several times in parallel for different values of lambda and R, basically. So there will be many matrices. For each one of them, we will apply this algorithm separately. Everything will be done in parallel. And at the end, we will choose one element. And I will also explain why it is safe to say that we will choose the element that we need. It will only happen under the assumption that there is a single heavy element, really heavy, in the sense that it's heavier than 100 times at every other frequency. And exactly what is the main idea that I explained before, because we always, if you look at this, right, we never overestimate, right? The frequencies that we will report will be this C sub I at the end, which can be at most the frequency of the element. Because it can be at most the frequency of the element, if we find a really heavy element at the end, it will be larger. It doesn't matter how many other games we will play, how many other matrices we will consider. If we find it is sufficient for us to find an element with, let's say, 2 approximation of its frequency. I wish I would have a blackboard here, but yeah. But just imagine the following case. This is our heavy element, right? If we are lucky enough to sample it in the middle, so at the end, when we have at least half of its frequency will be collected using this algorithm, right? Because what is going on here, every time that we keep the element, every time that we keep the sample, we keep counting, right? So in every row, we keep counting how many times we observe it, right? So imagine that in one of these matrices, we did sample heavy element 1, and it happened that its frequency is at least half the sampled frequency, the result of this counting, will be at least half of what we need. If this is the case, then we can safely discard everything else, right? Because the original frequency was much higher, was 100 times larger than everything else. And
assuming, because eventually you would want also to be with a case that it's 2, 3, 5 heavy elements.
yeah, absolutely. So it is.
Now you assume that there is only one.
Now I assume that all I want is 1, and then I will reduce the more general case to the 1. So it will be step by step, so on. So is this clear, more or less? Okay, so let me give you maybe a very small example that hopefully will illustrate what is here, right? So this is a 3x4 matrix, and let's say that in the first case we will sample 2, in the second case we will sample 3, and then we will sample 1. So if lambda is 1, so our results really depend on the parameters of lambda and R and T. So for example, if lambda is 1, then all we need to ensure that there is a linear growth, basically. So every time we see at least 3 or 4 numbers at the end of 3 rows. So in this case, 2 will win, because it will collect 3 elements by the end of the first row, and 3 will be sufficiently large to go through 3 rows. Okay. If you put lambda to be 100, right, then nobody will win in the sense that the last element will be sampled. Okay. Does that make sense? And the main theorem, basically, of this algorithm is the following: that if we have such a matrix, R by T matrix, and we know that there is a relation, the following relation between the frequency of the first element and the second residual moment and the third residual moment, then the probability that we will sample doesn't, regardless of the distribution of elements in this matrix, the probability that we will sample this first element is really a function of the frequency of the frequency and the number of columns, basically. And so it is basically what we're saying, regardless of the distribution of the data, it is the same. If we can get the right values of R and lambda, it is the same as what we did in the first slide. Okay, so basically sample from every row, and at the end you will get the heavy element with exactly the same probability. Beta t. Beta t. It's not so big, right? And the reason for that, I need this inequality somewhere in the analysis. But if this inequality is not true, then we are lucky, actually. Because if for the values of t that we consider, t is something like n to the 1 minus 1 over k. If our element is that heavy, it's trivial to find it with much smaller space. Okay, so this is what you see here is actually not such a bad case. Okay, and so I will not probably have time to prove this, but this is where the most work was done. Once, yes, absolutely. I will talk about the intuition. Let me just finish maybe the main steps.
But in the actual algorithm, you do it many times, right? Because this probability is still very small.
Yes. Right. This is only for one sample, of course. Yes, I will have to repeat it many times. Let me first show how I will apply this. So again, this is exactly the slide that we saw 10 minutes ago. If I choose now lambda in this way correctly, in a correct way, right? Assume someone gave me this value of lambda, that the previous theorem implies that if we have a heavy element now in the sense of the case moment, then this is the probability of to find it. Okay, so that's just by computations that I will maybe have time to show, but basically the more general theorem, if you apply it here, this is what we have. Now let me step back and explain how the algorithm will work. What we have seen so far is an algorithm to maintain a single sample in a single matrix. Okay, it does not imply, of course, immediately that we will find the heavy element, but this probability means that if we will repeat this n to the 1 minus 2 over k times divided by delta, if we will repeat it independently in parallel on this matrix, if we guessed the right value of delta, we are done. Exactly by the same arguments that we did before.
How small is delta?
Delta is actually large. So delta is this. So this number, this number is a ratio between the first moment and the case moment. So it can be anything from it can be anything from 1 to n to the 1 minus 1 over k, right? And so delta is also can be sufficient. We will only need, so now let's look at this. The problem is that we don't know delta, but we already have algorithms that work in this space with some logarithmic factor. So if delta is larger than log n, larger than log n to some power, then we are done. So we only need to run deltas from range from 1 to some log n, to some log n to some polynomial power. Okay. So this is what we will do. We will run this algorithm. So every time we will fix a delta, we will guess the value of delta, and run this many samples in parallel And at the end, we will have n to the 1 minus 2 over k divided by delta samples, right? Then we will compare the frequencies. And we will choose one sample with the highest frequency. And this will be our output. Okay? This will be the output of our algorithm. So what happens if we have a frequency that is significantly larger than everything else? First, we have a constant probability to sample it. And second, if we sample it, then with probability 1, it will win everything else. If we sample it at least in the middle somewhere. Does it make sense what I'm saying? So this is a very, very...
You try for delta, which is power of 2.
Yes, this is exactly what this is. This is power soft.
You said that you could stop, but it doesn't really matter.
It doesn't really matter, yes. Yes, 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 yes. Right. And so the total space will be n to the 1 over k. Let me see if I have it on the next slide. No, I don't have it. Yes, so the total space for this will be n to the 1 minus 2 over k times log n. Why? Because this will be geometric series that converge to n to the 1 minus 2 over k. And for each sample, we just will count. So what we will maintain for each sample is the ID, which is log n, and the counter, which is log m. Basically, that's it. Right? No. I could probably save the counter, right? So I could probably reduce the space for the counter, but not for the ID. I don't know. So I will still need to have log n.
Maybe even for the counter. Because maybe there are many of them, so you cannot do probabilistic.
Right. Yes. Yes. You're right.
So you claim the running time bound with an iterated log here, and said you're going to go over log n possibilities for delta in a geometric tree. So that gives the log n.
No, the log n will come from the next. This is geometric, so this will just go inside. Okay. So I don't know how much time is left for me, but 10 minutes. Okay, so I will do the following. The second portion, I just want to spend 5 minutes on the second portion. It's not that interesting, but it gives the complete picture of why the first part implies what we need, and then I want to spend 5 minutes on the intuition. So why, if we have an algorithm for heavy elements, it implies that we also can approximate the case moment. For the following reason, informally, right? So suppose that we are given this set of heavy elements. This is the heavy elements, right? And then we define a random variable, which is basically a sampling now. So we eliminate every element with probability half, right? And then we multiply everything that is remained by 2, right? So this is H is a random vector with pairwise independent uniform entries. And then if we have this estimator, X is an estimator of V, of the first norm of V, just the sum of, suppose that all we want to do is to estimate just the sum of all entries in V, right? And it is not hard to see by Chebyshev that this is a good estimator. If alpha is sufficiently small, then this is a good estimator, right? Does it make sense? And so we can, yes, I'm sorry.
What are the VIs?
Imagine any vector. So V is just a fixed vector. What I'm saying is the following. You don't need, suppose that you want to compute all the sum, or the sum of all entries, right? And right, so it's clear. Okay. So this is a general idea of what will happen. We will maintain T. This is a different T something like log n at the beginning, such random vectors with pairwise independent entries. We will maintain a Hadamard product of, so initially we start with our with our fixed vector, which will be our frequency vector. And every step we will cancel approximately half of the entries, right? And we will find heavy elements on each level. Every time that we cancel, so this is what will happen. We will cancel half of the entries, find heavy elements if they exist, and go to the next level of recursion, cancel another half elements, etc., etc. So if we start with log n levels of recursion, at every level we find all heavy elements that exist if they exist. Then this, simply by union bound, this will give us a good approximation. So we can approximate every vector at every step. And the key idea here is we can simply combine all the heavy elements. Essentially what all we need is to find at every level of cancellation, we need to find the heavy elements and then combine them in this special form. Basically what will happen, we will have just to cancel. If we sample it to the next level, we will have to cancel, we will have to subtract 1. If we don't sample, we will have to add 1. Basically this is the whole idea. This is a reduction from the sum to maximum to some extent. From the sum to maximum. I didn't show the reduction from many heavy elements to 1. Let me now comment on why. Yes, you're absolutely right. I didn't say why it is easy when we can find one heavy element, when it is easy to find many heavy elements. It's a very simple trick. The trick is the following. Create another hash function from your universe into, let's say, suppose that you want to find all alpha heavy elements. Create a hash function from a universe into 1 over alpha square. And then separate the stream into 1 over alpha substreams by hashing into different pieces, right? Then with high probability, each one of these heavy elements will become a super heavy in its particular substrate. Again, yes. So everything again is in parallel. Right? So at the end, this is the algorithm. So this is the algorithm that will reduce the max to the sum. So we will start at some level of recursion, level t, and then we will recompute. Basically, we will find heavy elements. So this is S sub I, means the set of heavy elements on each level of recursion, and then we will recompute it back to the norm. Now, and so log, the iterated log basically comes from the following fact. You can repeat it many times. You can repeat the same trick several times. Every time feeding your algorithm, your improved algorithm, as the basis of your recursion. So t originally will be log n, and then you can go from log n to log n to log n, etc., etc. Every time at the bottom of your recursion, you will apply the previously developed algorithm. I will not show why it works, but this is the idea. Yes, yes, absolutely, yes. Okay, so now let me maybe just, if I have 2 more minutes, I just want to talk about the intuition of this. This is the most interesting part of this work, right? I will only maybe talk about this portion. I will show why this is true.
So again, the statement is that if the first moment is just the sum of the entries between these bounds,
Yes.
then we have a good chance of finding.
Yes.
Yes.
Yes. The intuition is very simple. Imagine that in some row you have a noise. Let's say you have an element with a frequency n to some epsilon. Okay, and imagine that we sample this element. First of all, the probability to sample it is something like n to the epsilon divided by t, by the number of rows, right? So this is number one. Number two, how many elements we can kill using this. And this is where this linearity of liveness comes into the play. This element will only survive approximately n to the alpha rows. And on each row, it will kill at most, if we're talking about our heavy element, it will kill at most the same number of heavy elements. So in total, what we will see is the number of, let me just show you very quickly here. Yeah, that would be fantastic. Yeah, if we can. Oh, okay. That's how it works, I see. Should they just... Can I just... No? Fantastic. Oh, thank you so much. Oh, okay. This is automatic. I see. Okay. So imagine that this is you have here some bad noisy element L, 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 okay, and the frequency in the first row is n to the epsilon, and this is the entire frequency, so F sub L. Let's say the probability that is equal to L. Okay. Then suppose that we sample it here. If you remember the algorithm, it works as follows. Let's say that 1 is our good element, and we sample it here, right? If we are lucky, and this is I, and this is J, and if our tail frequency is larger than n to the epsilon, right, then by the definition of our algorithm, we are done. We will win, because yes, we will replace it, right? So let's now talk about how many good guys can be killed by this noise, right? Well, this many, right? So in every row, we can kill at most n to the epsilon good guys, right? And the number of rows that it will survive also can be something like n to the epsilon divided by lambda. Why? Because we request this q sub I. If you remember, this is exactly the number of rows that we can leave, that the sample can survive. So we always maintain that the counter C sub I smaller, larger than lambda times qi. So qi lambda q sub I is basically the number of rows that the sample will leave, right? And so he cannot leave for more than n to the epsilon. Okay, so what we have in total, that we have some random variable which is always smaller than n to the epsilon squared divided by lambda, right, because n to the epsilon rows, and the probability that y larger than 0 will be smaller than n to the epsilon divided by t. Therefore, the expected value of y, it's call it Y sub L.
That's where the third normal.
Yes, 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 yes. And then summing up over all of them, we will get the third moment basically. Okay. So the bound will be, so the right bound will be and in total you will sum up. This is where the third moment will come. Thank you so much.